Okay, so hi everyone. Okay, last lecture we talked about the filtering system in rectifier circuits, and we talked about the inductive input DC filters. Now we're going to talk about the capacitive input DC filters in this lecture. Okay. So let's look at the circuit where we have a capacitive input DC filter. So same as before, we have a diode bridge like this. Then we have a capacitor. And then we have the resistor. So R, C, D1, D2, D3, D4, and this is Vm sine of omega t is our input voltage, and I of S is our input current. So now let's look at the waveforms of this circuit. It's a little bit different than how that inductive one worked. So the analysis is also a little bit different. So if this is V of S, so it's a rectified, our V of S is a rectified voltage, like this, which is the input, right? The source voltage. And this is Vm, which is capital. And then I have my V of R, which is the rectified voltage here. And my V of R is, if I draw the V of S as these dotted lines, my V of R would be something like this. These solid lines here. And I of S, which is the current, would be something like this. So as you can see, the current in IS is either 0 or it's on at a very short time, basically. And during this time, a lot of current with a high peak current gets passed through these diodes D1, D2, D3, D4 based on which one is conducting at that moment. So in here, D1 and D4 are conducting, and in here D2 and D3 are conducting. Pi over 2 pi, 3 pi over 2, 2 pi, omega t, omega t, omega t. Okay, so when the instantaneous value of V of s is higher than instantaneous value of V of r, either d1, d4, or d2, d3 conduct, as we showed here in these two parts. And the capacitor gets charged. When the instantaneous value of V of s falls below the instantaneous value of V of r, all diodes are reverse biased. And the energy in capacitor is discharged through R. Okay, so when Vs here is lower than V of R, then what happens is that this capacitor here is discharging energy into the resistor, and you have this fall of VR because the VR is actually the voltage across the capacitor, so it's as it's discharging, its voltage is also going down, right? Okay, so now when Vs, the voltage of the source, actually goes above of V of R, then either of these D2 or D3 diodes, or D1 or D4, start conducting, and Is actually will have some inductor value, and this current will flow through the output resistor and the capacitor and charge the capacitor up, and then boosts this voltage back up again. Okay, and this will create a ripple, peak-to-peak ripple. Oops. So VRPP, which is the peak peak-to-peak ripple. And so this is this peak-to-peak ripple is due to that charge and discharge of that capacitor. So now the capacitor only gets charged at a very small time here, and which is called theta, or the conduction angle of the diodes. Now, as the ripple decreases, that means our capacitor as we increase our capacitor and the ripple decreases, so this conduction angle time also decreases. But what happens is that this current here will have a much higher surge, so the diodes have to be able to burden and a lot more repetitive surge currents that are going through D1 and D4 for the same amount of power level. So that's the drawback of having a very small peak-to-peak ripple voltage. This problem can be solved by adding LC filter at the source side here. So if you add an LC filter here, you can smooth the current out a little bit and make it a little bit better. But we won't get into that part. So in practice, if the peak-to-peak ripple voltage is small, VRPP, which is the peak-to-peak ripple voltage, can be approximated as so it can be approximated as VR peak-to-peak equals Vn divided by FR RC where FR is the output ripple frequency of the rectifier, where FR is equal to 2FI, which was the input frequency. Okay, now in order to find the average output, basically the average output voltage, can then be found as V out DC would be VR minimum plus, or V out minimum, which is the same as VR here, V max divided by 2. So our V max is actually equal to V of M, right? And then this would be if this was a linear, so this is again approximation. So if these two parts, so this part is more linear, but this part is not linear, but we can just approximate that, okay, these are all linear. So this is equal to Vm minus Vr peak to peak plus Vm divided by 2. So that's 2Vm minus Vm divided by Fr Rc divided by 2. Then V out dc is equal to Vm multiplied by 1 minus 1 over 2 Fr Rc. And the RMS output voltage V out RMS is approximately V out RMS equals Vm divided by 2 root square of 2 Rc Fr. Actually V out RMS and ripple factor. Is approximately this, and the ripple factor, as we have explained before, is equal to V out RMS divided by V out DC, which is equal to Vm divided by 2 root square of 2 Rc Fr divided by V out DC, which is from here, is equal to Vm 1 minus 2 Fr Rc, which is equal to 1 over root square of 2 Fr Rc minus 1. Okay, so let's look at another concept here, which is inrush current. So I think it's good that we touch a little bit on this concept as well, so that if you ever want to implement such circuit, you would know that. So let's consider if let's draw the circuit down here again very fast. So let's consider the first moment that you want to connect the diode bridge into the source. So let's say this is off at the beginning, and then we have this diode bridge here. Okay, and this is a capacitor, and then the resistor here. So when you turn this switch on, the first moment that you connect this voltage, so there's no charge that is across this capacitor. So the voltage here, there's basically no charge, and a huge surge current can flow through these diodes. And if that surge current is not within the limits of the actual allowable surge current limit of the diode, it will burn these guys out. So in order to mitigate that, we need to implement some sort of inrush limiting circuits, factors. Right, so that's the basic idea. So the inrush current is imposed on the diode during the instant when the diode bridge is connected to the supply. Inrush can be very high. Because the capacitor has zero charge initially. The worst case inrush current is occurred if the rectifier is connected to the source at the maximum voltage. So this is an AC voltage, right? So let's say when the time is right at its peak, we turn this switch on and we connect the diode bridge to our source. So this is the worst case, because because this is going to be the I inrush current that we're going to see. So the I inrush at the worst case, so I inrush would be equal to V of M, which is the capital of this guy, V of M sine of omega t, okay, divided by whatever RESR, which is the equivalent series resistance of the capacitor that is there. Which is usually a very small value, so you would have a very high inrush current. If you have other resistances in path here, such as the resistance of the wire, so you can put that into effect too. Sometimes you use a low frequency inductor here, and then connect that inductor to the diode bridge. In that case, the resistance of the transformer wires are very high, and usually you end up with not as high as in inrush currents anymore. So you won't need to worry about that anymore if you have that low frequency inductor in between here. But when you connect your main grid, for example 110 volts at 60 hertz directly to your diode bridge, usually you need to worry about the inrush current and do something to limit that inrush current. Otherwise, if you don't if you connect at zero here, there will be no problem because VM here would be 0 and you won't have any inrush current. But it's just a matter of luck, right? So if you connect that switch in here, that's when you see that interrush current, and that's when it might actually blow up your diode. Okay, so to limit that, typically limited by adding a resistor in series with the source. But this usually causes a lot of loss. So what they usually do is they use a PTC and a relay, or they use NTCs here in order to limit that inrush current. So if you have a resistor, for example, with R inrush, so your I inrush would change to VM divided by RS, R plus, so that R inrush, that resistor that you put in series here, R inrush. Okay,